I have a formula involving the covariant derivative v sub j. Now I take the cross product of gi cross gj, and remember gi cross gj, that brought in this permutation object, epsilon super ijk times g sub k, involving then the covariant derivative, as we had last time, of the vector field v. So we're essentially there. Now we have a representation of curl v in an arbitrary curvilinear coordinate system. By the way, this expression can be used to establish that this epsilon here is in fact a third order tensor, or the contravariant components of a third order tensor. Previously, we had not established that. The reason being that everything else in the equation has the tensor property, that is, the covariant derivative, that gives you the covariant components of a second order tensor with the transformation formula that we discussed previously. Then we have the transformation formula for the g's. Curl v is independent of any coordinate system, so these must transform as the components of a third order tensor, and you will investigate that now in your new homework. You won't, not for this specific tensor, but for a third order tensor in general. Okay, so that's this is very similar to the Cartesian formula, which would just be an E ijk bj comma I with an ek over here in Cartesians. Well, it's important for our later work to define the curl of a tensor. So it's quite rare in continuum mechanics that we need to be concerned with the curl of a tensor field. However, in this subject, in plasticity, we will see later that the curl of a tensor field plays a fundamental role. In fact, it will allow us to define a dislocation density associated with dislocations induced by plastic deformation. So we will depart from common practice and discuss the curl of the tensor field. In this case, a second order tensor field. We'll write it again, CURL-A. And the curl of the tensor field is itself defined to be a tensor field, a second order tensor field, such that when you operate on a fixed vector C, you get the curl of the vector A transpose C. And we can now use our formula for the curl of a vector to figure out what this looks like. So this is just a definition. The first line is a definition. C is fixed. To take the curl of a vector, I can use this top line here and just invoke this definition, this result. A transpose C comma I, use the fact that C is fixed. Well, A comma I itself, we know in terms of the covariant derivative, in this case, making use of contravariant components of A. There are 4 representations of A, contravariant, all covariant, or left mixed, or right mixed. Here I'll just take this one representation for now. And so we know this in terms of the covariant derivative and the basis here. So let's see, we need the transpose of this. A transpose comma I is the same as A comma I transpose. As I mentioned last time, taking the derivative of a tensor with respect to a parameter, in this case the ith coordinate, commutes with the operation of transpose. So I can just take the transpose of this, which is the same as interchanging the factors in the tensor product. So I can do that here. And then I have to operate on C, and so I do that here. And that converts the tensor product operating on C to a dot product, Gj dot C. And then we need to insert that into this formula. We do that here. And I get G super I from this term cross G sub K. That's a little bit awkward. We haven't defined that operation before. What I can do is I can regard G sub k is the indexed lowered version of G super L using the metric. Okay. And then I have the Gj.c carried over. And from last time, remember the so-called Ritchie Lemma, which says that the metric is constant with respect to covariant differentiation, combined with the product rule for covariant derivatives. I can just put the G inside the derivative, pass it through this derivative. And when I do that, I can now sum on K and regard this combination as the left mixed component, A, J, L, with the J first and the L second. That's why I put the dot here under the J to reserve this first space for the index J, okay? Because the order of the indices, which comes first, actually matters. So I get a the covariant derivative of the left mixed components, which you can work out. I didn't give it to you explicitly last time, but you can work it out easily using our notes from last time. Then this GI cross GL is the permutation, now tensor, permutation tensor epsilon ILM GM. And I carry this term. Now I can extract a tensor product operating on C, right? And compare both sides, compare this to the definition here on top, using the fact that C is arbitrary, and I get immediately this expression for the curl of a tensor field. Okay? And we'll make extensive use of it later on. Let's review so-called Stokes Theorem, as it's usually discussed in Euclidean space. So this is the version of Stokes Theorem that you learn in courses on advanced calculus, and I'm sure you've seen this before. Suppose you have a surface in space with a boundary, called a boundary curve gamma. And we'll say that S is an oriented surface. That just means that one can define a normal that's that's piecewise continuous on the surface. A piecewise continuous allows you to have a faceted surface, like in the shape of a diamond, let's say, the surface of a diamond, where you have patches within which the normal is continuous. Okay, we'll take this surface to be simply connected, which means you can take a closed curve in that surface and reduce it to a point without leaving the surface. So there are no holes in the surface, in other words. And if we have a look at the surface normal evaluated at the edge here, gamma, we can construct a basis. Here we have dx, which is the tangent to the curve, times ds. So here I'll use an arc length parameterization. S is arc length along the curve. T then would be the derivative of x with respect to s, and it's a unit vector. With n and t thus defined, I can take a cross product and define a normal to the edge, which is orthogonal to the surface. So a normal to the curve orthogonal to both n and t. So we're going to traverse the curve in the sense shown here, such that T, N, and nu define a right-handed orthonormal basis at every point on the curve. And suppose we have a vector field Vx defined in space surrounding this surface and hence also on the surface. Then Stokes theorem, and I won't prove it, but because it's classical and most students in the sciences see this derived in other courses, says simply that the circulation of V around the curve, which is the integral of V dot x, a path integral around the closed curve, traversed in this sense of increasing arc length, is the integral over the surface of the normal to the surface at every point, dotted with the curl of the vector field integrated over the surface. So first thing we can do is extend this classical theorem to tensor fields by, for example, supposing that V is a tensor field A transpose operating on a fixed vector C. Then this integrand here, v dot dx, is simply c dot a dx. Right? It's dx dot a transpose c, which is the same as c dot a dx. And so this left-hand side, because c is fixed, I can extract it from the integral, and I have this path integral of a operating on dx. Well, alternatively, I can use the fact that c dot a dx is the same as a transpose c dot dx, bring c inside the integral. C is fixed, so I can do that. And then use the Stokes theorem to write this. This is my vector v, so that would be n dot curl of v integrated over the surface. Whoops, excuse me. And from the definition of the curl of the tensor, that's the same as the tensor curl A operating on C, that we've just had that. And I can rewrite this as curl A all transpose on N, dotted with C, using the definition of transpose. Dotting with C is convenient because then I can extract it as a dot product outside the integral because it's fixed, compare with this side of the equation. This is true for any choice of the vector C. Therefore, this integral has to equal that one, and we have now an extension of Stokes' theorem to tensor fields involving the curl of the tensor A. And we will revisit this a little bit later in the course, apply it extensively. Okay, I want to discuss a more fundamental version of Stokes' theorem, which doesn't require any underlying geometry. Here we've made extensive use of geometry. We have the idea, the concept of surface area, arc length on the surface, and so on. It turns out the Stokes' theorem has a more fundamental interpretation, which requires no such geometric concept. We can derive that fundamental version from this special version, which is valid in Euclidean space, the space of Euclidean geometry. Let's look at a point on the surface that we've just discussed. And so we'll describe the space using our curvilinear coordinates, theta super I. We can parameterize the surface by giving the 3 space coordinates as functions of 2 parameters that parameterize the surface. Is there a question? Okay, so you can think of coordinate curves, say u super 1 and u super 2 coordinate curves etched on the surface, passing through the point P. And we'll have a normal NDA, which is so surface measure is really an oriented surface measure, NDA, on the surface. So if we put this parameterization into, say, our position function in space, then we have a vector valued position function of the 2 parameters ultimately by giving these theta i's as functions of u1 and u2. So this left-hand side is the parametric representation of position on the surface. Okay, well, I can imagine looking at differentials induced by differentials of u1 and u2. For example, dx1, I'll call gi d theta I. We know dx is gi d theta I, but since I'm going along this one direction, I'll call it d1, d theta 1 I. And dx2 here, gi d theta 2 I. I'll define what these mean in a moment, the d theta 1 and d theta 2 I. The normal then, so these are tangential to our coordinate curves on the surface. The oriented normal is just the cross product. So the cross product of these 2 vectors gives you both the orientation n and the area enclosed by this parallelogram tangential to the surface. So I'll write dx1 is gi d psi I. D psi I is d theta 1 I. Okay. And dx2, all right, is gj d eta j, where d eta I is d theta 2 I. So here's what I mean by these. D psi I is d theta 1 I. But that, by that I mean hold u2 fixed, so we're in a curve of constant u2. So the d theta I here is partial theta I with respect to u1 times du1 by the chain rule. D theta 2, which I'm calling d eta, is likewise associated with a curve on which u1 is constant, so I'm on this curve here. u1 is constant on that curve. So this, by the chain rule, this is just d theta du2. And so that I don't have a cumbersome notation with these parentheses on top, I'll just write them d theta I and d eta I, okay? Okay, so now back here, I now have a cross product, gi cross gj, d psi I, d eta j. The cross product brings in the permutation epsilon I j k g super k, and so on. Okay, so you could think of dx1, that's the same as r comma 1 du1, because that's the same thing here. This is d theta I du1, that would be r comma 1 du1. So you can alternatively think of dx1 as r comma 1 du1, and so on. Okay, so let's have a look at what happens with Stokes theorem. We'll use this representation for curl V, three-dimensional vector, curl V, dotted with n as required in Stokes theorem. Here is our NDA, is just epsilon d psi I d eta j gk, and then dot with the curl of V right here. This again is a scalar triple product, so I can interchange the cross and the dot. And now I have another permutation, epsilon super klm g sub m. And then I dot with v comma l. So that's a lot of summation going on, right? I've got a sum on k, I, j, l, m. So that's an enormous number of separate terms appearing in this sum, in this line here. So although one has to be quite careful with the summation convention, you should appreciate just how compact it is compared to writing this entire mess out longhand. That would take a lot of paper. Okay, I'll assume now you've seen something before called the epsilon delta identity, which we certainly cover in 185 and 287. It's a simple identity involving the permutation symbol. Whenever one index is repeated, as it is here in the permutation, in this combination of permutation tensors, the k is repeated. This combination, the two epsilons together, form this parenthesis involving only Kronecker deltas. Kronecker delta Li mj minus Lj mi. So there may be one or two of you who have not seen our courses in continuum mechanics, may not be quite familiar with this. It's a standard identity, and you'll find it in any introductory book on continuum mechanics. It's extremely, pardon?
Excuse me, Professor.
Yeah.
So if both of those epsilons, all of the indices were in same level? Yeah.
Then it wouldn't be undefined. It would make no sense. That would be okay in a Cartesian system.
Okay. So
now,
we don't, okay.
Actually, it's still okay, because the epsilon with all the indices downstairs is square root of g times the standard permutation symbol.
Right.
The epsilon with all the indices upstairs is 1 over square root of g times the standard permutation symbol.
True.
And the standard permutation symbol with upstairs indices we define to be the same as the one with downstairs indices.
Okay, I see.
So it would still be fine in that case.
I want to see that if there are any combination of epsilons that instead of delta we get metric tensor.
It could be. No. Okay. In fact, there are identities involving the metric tensor and the permutation. symbol.
Okay.
Yeah. This is one of those. This is one of those identities, the epsilon delta identity. Okay.
Okay. Yeah.
But there are other identities. For example, with all indices upstairs, you could raise all the indices, right?
Besides one of them, because
using, if you wanted to raise all the indices, you'd use the the reciprocal or dual metric tensor 3 times, one for each index. And then you'd have a result that involves metric tensor. Okay? So you can, in fact, you can immediately deduce those identities from this exact expression. Right?
Okay, thank you.
Yeah. So then this is nice because any operation involving the Kronecker delta is very simple. We carry over everything as before. For example, sum on I here, and you get d psi L. Sum on J, you get d eta M from the first term. Then you get minus d psi M by summing on I. Sum on J, you get d eta L, right? And then gm dot v comma L. This again is too much writing, too much to write down. So people use this notation with a wedge in between d psi L and d eta M. This is called the wedge product. And this is a standard notation in differential geometry, especially in the more modern literature in differential geometry, called the wedge product. And so in a sense, it encapsulates the notion of surface area. Right? An oriented surface area involves the wedge product of these coordinate differentials with the basis. The interesting thing about it, if anything, is that it's skew symmetric in the indices. Right? If you wrote down d psi M wedge d eta L, right? You put an M here, an L here, and an L here, and an M here, you would just get the reverse of what we started with. So this has a skew symmetry property with respect to the indices. Interchanging the indices means introducing a sign change, okay? So there's a skew symmetry, which you should remember. So we have now gm dot v comma L, d psi L wedge d eta M. And this is nice because we have now a sum on L and M, right? Because this is skew symmetric in the indices, the summation only sees the skew symmetrized indices ML. In other words, it only sees the skew part of this with respect to the subscripts M and L. Such a thing I will denote using square brackets. Square bracket around the M to the left and around the L to the right. So that's also a completely standard notation. I'm not just making up new notation as we go, I'm just using standard notation. So this box here is intended to denote skew symmetrization. So for example, if you have a matrix A sub ML, A box ML means the skew symmetric part of AML, okay? Just like usual. Okay, so now this involves a partial of V with respect to L. We can write that in terms of this covariant derivative, VI semicolon L, GI. Take a dot with GM as required in this formula. That just gives us the covariant derivative VM semicolon L, which is, if you recall, is a partial derivative, and then we have these connection terms here with connection coefficients. Again, the L goes with the second index on the gamma, the connection coefficients. Now I only need the skew symmetric part of that with respect to the indices ML. So that's the skew symmetric part of this covariant derivative. That's V, the skew symmetric part of the partial derivative. Over here, I would take the skew part of M. So the skew part of the connection coefficients with respect to the lower indices. But if you remember, since we've done our theorem here, we've introduced it, Stokes Theorem in Euclidean Space, the connection coefficients are symmetric in the subscripts. in Euclidean space. So these drop out after skew symmetrization, and you just get the partial derivatives. On the other side of Stokes' theorem, on the other side of the equation, we have the circulation around the curve, gamma. That, of course, we can write this way, and that just brings in the covariant components times d theta I. So Stokes' theorem reduces now to this. Here we have the wedge of the coordinates, partial derivatives, and here we have vi on the left. So here, the first factor is what I called before dec psi L. It just means this: you're on a U2, you're on a curve U2 equal constant. So this differential is just this. This one, we're on a curve U1 constant. This is what I called before d eta m. So I've reverted to this notation because this is the one you see in textbooks on differential geometry. And what's interesting here is notice that this form of Stokes' theorem involves no geometry whatsoever. There's no notion of length or area or connection. The connection has disappeared. Right? No notion of metric. Those are all geometric concepts. Metric is used to define volume, area, length, and so on. No notion of metric, no notion of connection. So this is a theorem in pure analysis, pure calculus. It has nothing to do with geometry. And in fact, it's the fundamental version of Stokes' theorem, which is valid because there's no restriction to any geometry here. It's valid on any manifold whatsoever, Euclidean, non-Euclidean, doesn't matter. And if you're reading, if you're interested in pursuing differential geometry further, you would eventually study the calculus of differential forms, so-called. On the left, we have what's called a one form. Think of it as a covariant vector field integrated against the coordinates. On the right, we have what's called the exterior derivative of that one form, the exterior derivative involving this wedge product and a partial derivative. The comma L goes with the first differential. The M in front goes with the second differential. So this is the fundamental statement of Stokes' theorem. Nothing to do with Euclidean geometry whatsoever. So it's extremely general. Okay. The classical Stokes theorem you get in Euclidean space that we started with, because we're familiar with it, is obtained simply by reversing the steps from this result to go back to the classical Stokes theorem. Okay. So I want to make use of this general version of Stokes theorem to introduce a further geometric concept called the Riemann tensor, which we're leading up to here. So as an example of the application of Stokes theorem, let's imagine we have some vector field defined on a curve. The curve is parameterized by giving the three coordinates as functions of the parameter, not necessarily time, just any parameter. And so U is defined then on the curve. If U is we can imagine if U is a function of the coordinates and the coordinates are functions of t, then U is ultimately a function of t. Although actually, we don't even need U to be a function of the coordinates, we just need it to be defined on a curve as a function of one parameter. Let's call that curve gamma. And we know intuitively what we mean by a vector field remaining parallel to itself if we move along the curve, right? If we move along the curve and the vector is unchanged as we move along the curve, it's the same magnitude and direction, so that at every point on the curve, we're just we're transporting the vector in a parallel manner so as to preserve its length and orientation. That means simply that the vector field has no derivative with respect to the parameter. It doesn't change along the curve. So let's explore the implications of this idea. This is called parallel transport of a vector field along the curve. And this notion of parallel transport plays a very fundamental role in the development of differential geometry and extensions of Euclidean concepts to other kinds of geometry. So we'll introduce our basis decomposition of the vector field, let's say in terms of contravariant components. The dot is just a conventional ordinary derivative. Of course, that obeys the product rule. So we have these two terms. We have G dot is gamma in terms of gamma and theta dot J. Remember last time we talked about an affinely connected space, of which Euclidean space is an example. And so let's see, if I relabel the summation index, call it K so that I can group the terms together, I have this parenthesis. And because the G constitute a basis, the only way this can happen is if the parenthesis vanishes for each K equal 1, 2, or 3. If I now multiply this equation through by dt, I can rewrite it in this way. So this is the equation of parallel transport in terms of components of the vector, contravariant components of the vector. And that's a system of 3 ordinary differential equations. So provided the gammas are defined on our curve, they're defined in terms of the thetas, the coordinates, but the thetas are given as functions of the parameter on the curve. So this then becomes a system of linear ordinary differential equations on the curve. If you give an initial condition for the UKs at some point on the curve, then the highly developed theory of ODEs establishes that you can find that this has a unique solution. Okay. However, this does not establish the existence of the field UK as a function of coordinates in the space surrounding the curve. Okay. So it does not establish that this is integrable to give a vector field defined in the space, right? This only integrates to give a vector field defined on the curve. We're interested to know what conditions should be satisfied in order that these equations here in parentheses can be integrated to give the contravariant vector field UK in the space containing the curve. In other words, to give the contravariant vector field as functions of the 3 coordinates parametrizing the space itself. Well, we can look for necessary conditions for that to be the case. If there were such a result, if the U's were defined in the space, then the dot here, appearing here, would just, by the chain rule, would be the partial derivative of UKs times theta dot, okay? In which case, this equation would now become this one. And here we recognize our covariant derivative formula. So integrability in space would mean that it doesn't matter which curve we integrate on, we would get a vector field defined in the space containing the curve. That means this should hold for arbitrary curves, which means arbitrary parameterizations of the curve, of parameterizations of any curve, I should say. So the theta dot j's are then arbitrary if the curve is arbitrary. Okay, so the theta dot j's are really pointing in the direction of the tangent to the curve. And so passing through a point, you can imagine different curves would have different tangents. So this would hold for arbitrary tangent vectors theta dot j. If these are arbitrary, you can choose them, say, you could choose theta dot 1 to be the number 1, let's say. And then this would, the parenthesis would have to be 0 when j equals 1. A different curve, you could passing through the same point. So this only depends on the point through which the curves pass. This gives you the direction of the curves. You could pick theta dot 2 equals 1 and all the others 0, and this would have to be 0 then for j equals 2, and so on. So this would then have to be 0 for all j. In other words, you'd have to get this. So parallel transport of a vector field defined in the space means the covariant derivative of that vector field is 0. In other words, the vector field is constant in space. And this simply gives you a set of differential equations then to solve for that vector field, partial differential equations. Suppose we're looking for a C2 vector field so that the UKs are twice differentiable with respect to the coordinates. That means UK comma JL, let's say, which would be the L derivative of this, would have to be equal to the UK comma LJ, which would be, so you replace J by L and take a J derivative. So those would have to be equal. Okay, that's just the restatement of this, what I've just mentioned. So this equality turns out to have an interesting consequence, which we'll get to on the next page, and which I'm going to ask you to work out in your new homework. We'll get to the same conclusion by using Stokes Theorem. So instead of working out the implications of this, which I will ask you to do in homework, let's use Stokes Theorem to examine the implications of the integrability of this equation, right here, this set of equations. If this set of equations is integrable, that means, for example, duk is an exact differential, because then duk would be uk comma L d theta L. Being an exact differential, its integral along a path would just be the difference of the values of uk at the two endpoints of the path. If the path is closed, those two endpoints are the same, so the closed path integral would be 0. Okay, let's put a minus sign in front just to make it easier to use this equation here. So if I use that equation I just mentioned, duk is gamma k I j ui d theta j. For k fixed, so we have, just ignore k for the moment, we have this whole thing we could call v sub j d theta j, right? There's a sum on I. Suppress k for the moment, we have, this defines a vj, v sub j d theta j. We can use Stokes Theorem on that. We convert that to this surface integral involving this wedge product. That involves, first you take the L derivative of the v sub j, that's this, and then you form this wedge product. Now you're integrating over the surface. Now I just use the product rule for partial derivatives, and I get this. Ui comma L, according to the equation of parallel transport, I can invoke that to rewrite this in terms of the connection coefficients and vector field itself. Okay. Let's see, I have a U super M here and a U super I here, so why don't I change the summation index here from I to M? I'll just call it M, so that I can factor out the UM from both terms. And I get this integrated with respect to this wedge product. Remember, the wedge product is skew symmetric in the indices L and J. So let's see, when I sum on L and J, K is fixed in the entire discussion. It's not participating, it's playing a passive role. It's not participating in any summation. M is summed, J and L are summed, okay? The sum on J and L will only see the skew symmetrized part of this parenthesis with respect to J and L. So I'll indicate that by inserting the box J comma L. Remember, that means skew symmetrization. Here I've got a skew symmetrized with respect to J and L, but M is in the middle. So I use this notation, which is also standard. I'll put a box around J and L, but I'll put some bars around M to protect M from the skew symmetrization operation. So this vertical bars surrounding M just means that M will not participate in the skew symmetrization processes. We just leave M alone, as shown here. This is the definition of this strange notation with 3 indices and a box surrounding the middle one, or vertical bars surrounding the middle one. It just means we are required to leave this index alone, not disturb it, when we do this skew symmetrization with respect to the remaining indices. But that's just the meaning of that notation. Like we can introduce also a symmetrization operation while we're at it. The round parentheses will mean symmetrize with respect to J and L. So we have 1/2 A JL plus ALJ, and the middle index is protected by these bars here. It will not participate in that symmetrization process. If you read books on tensor analysis, this notation is also completely standard, which is why I'm using it. Okay, so after all this, barrage of indices is you can think of all the summations going on as a kind of smoke screen that looks rather impenetrable. So rather than write all this business down all the time, we'll just give this stuff a name. We'll call it R super K MLJ MLJ U super M, then the wedge coordinates differentials. And we'll put the half in front. Here R, this is a 4-index quantity, KMLJ, is simply this parenthesis here with a factor 2 restored, okay? And the reason for the factor of 2 is the skew symmetrization operation brings in the factor 1/2, which can then be annihilated by that too. So that's just a definition of R, which is such that this integral equals this one. So we have this complicated looking expression involving not only the connection coefficients as products, but also their partial derivatives in this combination. So we're skew symmetrizing with respect to J and L. So that gives the JL, which we had here, minus LJ, and then skew symmetrize with respect to J and L here, but we don't touch M. We just interchange I and L, and then the skew symmetrization brings in a minus sign with a half that goes with the 2 to give us this. That we could simplify matters slightly by just passing the minus sign through and rewriting that this way. Okay. So this R business plays a basic role in ensuring the existence of a contravariant vector field in the space defined by parallel transport of the vector field. So it looks like, okay, we want this to be 0, right? If there's a vector field in the surrounding space, then this should be an exact differential. It looks like a sufficient condition for that to be true is if this R business we've just introduced is 0. That guarantees the existence of that vector field defined by the parallel transport operation. So we call this is a very important tensor because it's called the Riemann tensor. And the R notation comes from Riemann, who basically invented the idea, and when he invented Riemannian geometry, this Riemann tensor, or its antecedents, emerged in the course of that development. And in homework, I'm going to ask you to show, although I have not done it here, that this is in fact a 4th order tensor. That is to say, these components obey the 4th order tensor transformation formula that you will derive in your homework. Okay. Just from the definition, we can note that it's not as horrible as it looks, because this thing is skew in J and L, right? So that means if we symmetrize in LJ here by putting a round parentheses around L and J, that means symmetrize in accordance with this definition, right? It just means so this would just be 1/2 the LJ plus the JL. That's equal to 0. That's immediate from the definition. It's already skew in J and L, so the symmetric part in L and J is equal to 0 identically. Okay. So in order to get this to be an exact differential and hence this integral to be 0, it's sufficient that this so-called Riemann-Christoffel tensor should be 0. That guarantees that we have, by integrating the equations of parallel transport, we can do that to define a vector field in the entire space. So the thing I mentioned on the previous slide here, this, I'll call it this equation star, carrying out this equality, I'll call that here the exercise, show that that's equivalent to this, with the Riemann tensor we've just defined. I'm asking you to just do that in homework. It's just an exercise. It's no big deal. Okay. Okay. In fact, this Riemann tensor is associated with curvature of the space in which it's defined. The reason for the name curvature is that if we look at the differential geometry of curved surfaces, that's a two-dimensional manifold. A characteristic feature of curved surfaces is that the Riemann tensor defined on that surface is non-zero in general. For a 2D manifold, the indices just run from 1 to 2, so there are a lot fewer of them to worry about. And in a general surface, the Riemann tensor would be non-zero. There are exceptions to that. For example, on a flat surface, like a plane, the Riemann tensor is 0. That's also true on cylinders, cones, and so on. So for certain special surfaces, the Riemann tensor is 0, but in general, it's not 0. And since those surfaces we associate with the idea of curvature, the name stuck, and this Riemann tensor has been also called the curvature tensor. It's more interesting, for example, in 4 dimensions, in space-time, it turns out general relativity is associated with a non-zero Riemann tensor. So we think of space-time as being curved for that reason. It has a non-zero Riemann tensor, and that's associated with the presence of gravity. And so this Riemann tensor plays an absolutely basic fundamental role in Einstein's general relativity theory. So it's in our flat space of our common experience, we're living, at least locally here, in a flat geometry, that's Euclidean geometry. The Riemann tensor vanishes. Okay. So far, we've only considered geometries of this type. Our Euclidean geometry is of this type. The connection symbols are defined in this way. That's how we define them. And our Riemann tensor depends intimately on these connection symbols and their partial derivatives. And in fact, in Euclidean space, we have the further condition that the GIs are the partial derivatives of position with respect to the I coordinate theta I. Later on, we'll encounter a space like this, with connection symbols given like this, in which the GIs are not the partial derivatives of any vector field. We'll talk about plasticity. So let's look at examples of spaces with this kind of connection coefficient. Euclidean space being only an example, not the only type for which this is true. So here we have these gammas. There are actually 27 of these altogether because each index runs separately from 1 to 3. So we have 3 to the power 3 terms here in general. These are then, according to this equation, determined by the GIs, right? Because knowing the G's, we can take their partials, of course. If we know these functions of the coordinates, we can compute the metric, hence the dual metric, and then compute the dual basis, all from knowledge of the G's. So here's another example of my senility. These are really 9 functions, right? There are 3 vectors, and each vector has 3 components. So there are 9, not 6, so please correct your notes. That 6 should be a 9. So we have 27 functions determined by 9 functions, right? So there must be some connection among these. There must be some relationships among these connection coefficients. Otherwise, because ultimately all of them are determined by only 9 functions. So a geometry like this places a kind of severe restriction on these connection coefficients, even in the non-Euclidean case for which this is not true. Or even actually, yeah, even whether Euclidean or non-Euclidean. Let's explore what those relations are. Well, in the definition of the Riemann tensor, we have partial derivatives of the connection coefficients. Put them in here and just take the partial derivatives using the product rule. We also have products of the connection coefficients. I'll use a kind of trick here. I'll write gamma super K sub IL as KSL Kronecker delta SI, so summing on I gives me this. That will allow me to interpret the Kronecker delta as this dot product using the duality relation or the reciprocity relationship between the natural basis and the dual basis. So I'll collect terms here. I'll write gamma IMJ GI, that gets dotted with gamma KSL GS. Gamma IMJ GI is just GM comma J, right? From what we've done before. And then we carry over this term. But this we can interpret as minus G super K comma L. Remember, the partials of the dual basis bring in minus connection coefficients. Okay, so we have this. The reason I've gone through this exercise is because now I notice that this if I add these together as required in the definition of the Riemann tensor, this will annihilate that, and we'll just be left with that. So add them together, we just get this last term here. The Riemann tensor is the skew part of this with respect to J and L and J, right? From the previous page. Right? We skew symmetrize with respect to J and L to get this Riemann tensor. And then we need the factor of 2, as shown here. So here's the factor of 2 over here. Skew symmetrize this with respect to J and L, and you just get this. The skew symmetrization just involves the partial derivatives. Now, if the G's are C2 vector fields, that being the typical case, then GM comma JL is the same as GM comma LJ. You can interchange the order of the second partial derivatives. So then the skew operation would vanish identically, right? Because these things would be automatically symmetric in J and L. So the skew part would be 0. And that tells you that the Riemann tensor is 0. But notice that in this deduction that the Riemann tensor is 0, all we used was this formula for the connection here. We did not use this. We did not use the idea that G is the partial of the position with respect to the coordinates. We made no use of that. So the Riemann tensor is 0 even if this is not true. In other words, for example, if this were true, then GI comma J would be X comma IJ, which would be the same as X comma JI. And so GI comma J would be GJ comma I. But we made no use of this. So this is true even when this symmetry does not, even when we don't have symmetry in I and J here. So in other words, even when the skew part, G box I comma J, is non-zero, but G box I comma J, put a box around I and J here, we'd have to put a box around this, and these would then be non-zero. So the Riemann tensor is 0 even when the gamma super K box IJ is non-zero. Of course, it is 0 in Euclidean space, but we made this calculation without that limitation. In fact, this skew symmetric part of a connection, which you can have in a general space, more general space, is also a tensor. It's a third order tensor, which is called the torsion tensor of the space. Okay. And in your homework, I'm asking you to consider the possibility that the space we're talking about has a non-zero torsion tensor. So the dot here is intended to mean the k comes first, is the first index, and I is the second index, j is the third index. So we use the dot to reserve the space taken up by k in the ordering of the indices. Okay, so in homework, I'm going to ask you to show something kind of remarkable. I'm going to ask you to show that the gammas themselves are not the components of a tensor. If they were, then the gammas here would be some third order tensor, and this would be the mixed representation with one index up and two indices down. It transpires, however, that the gammas are not the components of a tensor. Why? Because they do not obey the tensor transformation law that a third order tensor satisfies. However, when you do this, when you skew symmetrize in I and j, the result is a third order tensor. The result of this skew symmetrization produces a quantity that transforms as a third order tensor does under coordinate transformations. And so it is therefore a third order tensor, and that's called the torsion tensor. The tensorial property of variables that we use in any theory is extremely important, because if we use variables that are not tensors in an equation, then a mere coordinate transformation would destroy the equation. It would give us an equation that has no relationship to the original equation, just by transforming coordinates. We don't want physics to depend on our choice of coordinates, so we have to use tensors to ensure that any statement that's true in one coordinate system remains true in any other coordinate system, as a physical law should, right? Because the choice of coordinates is up to us, and nature presumably doesn't care about our choice. Okay, I'm saying too much in one breath here. So the upshot is that this so-called torsion is indeed a tensor. You'll show that in homework. So a space with this kind of connection will have zero curvature even if it has non-zero torsion, T. Okay. Our Euclidean space is an example of a space in which both the torsion and the curvature are zero. So a flat space, that is one with zero Riemann tensor, no curvature, and one that has no torsion, torsion-free space, is locally a Euclidean space. That is to say, everything can be derived, all the geometry can be derived from a position vector as a function of the coordinates. We see that here. For example, gm comma j would then be x comma mj. According to our definition of the connection symbols, that would also be this. Skew symmetrize in mj, if this is a C2 position field, you'll get 0. Carry through the skew symmetrization here, you get the torsion, sum on k. These are form a basis, therefore the torsion components are all 0 in a Euclidean space. Okay. So that means a space that does have torsion does not have a position field associated with it. There's no position field in a space with torsion. We can see that in this way. For example, on a curve, of course, we can always parameterize the curve by t. The derivative of some, we can introduce a vector field x dot, which is given this way along the curve. Right? That's position on the curve, in other words, is the basis times the dot of the coordinate. In other words, this is dx is gi d theta I, the same equation. Okay. If we look at the closed contour integral of dx, if dx were an exact differential, so that it would be the derivative of some vector field x, then this closed contour integral should be 0, right? Around a closed curve. let's put this in there. That's gi d theta I. Use Stokes theorem. So we have 3 vectors here instead of 1. 3 VIs, in other words, like V1i, V2i, V3i, associated with the fact that this vector, each vector has 3 components. Let's use Stokes theorem. This wedge product only senses the skew symmetrized part with respect to I and j, which brings in the skew symmetrized connection coefficients, sum on k then. This is our torsion tensor. So if the torsion tensor is non-zero, then this surface integral will generally be non-zero, which means this will be non-zero, and dx is then not an exact differential, which means there's no field, there's no position field who's different associated with this dx. In other words, dx, the equation dx, which is essentially this on the curve, is not integrable to give a vector field in the entire space. Okay. So in fact, the vanishing of the torsion tensor gives you the conditions under which this can be integrated to give a position field in the surrounding space. Later, we'll see in our theory of plasticity, the torsion tensor is nothing other than a density of dislocations induced by plastic deformation. So that because of that, this geometry associated with torsion will play a fundamental role. Okay, let's stay with this geometry defined by these connection coefficients. A moment ago, we had this formula for the curvature. We can observe that these are simply the projections of these vectors here, gm comma jl, box jl, into the dual basis. Those define the vector itself for each fixed mj and l. We project it into the dual basis multiplied by the natural basis, sum on k, and we just get the Riemann tensor gk with a half in front. So this shows us that, in fact, the vanishing of the Riemann tensor are the integrability conditions for this set of equations that we had before. Last time we talked about an affinely connected space being one for which this is true on curves in the space. If this can be integrated, the system can be integrated to give you the GIs as C2 functions of coordinates in space, then this would have to be 0, which means the Riemann tensor is 0. So the vanishing of the Riemann tensor are the integrability conditions for this system, which is true in any affinely connected space. Okay. If the Riemann tensor is not 0, all that we can do is say that these equations can be integrated on a curve, rewriting this in this form using the derivative with respect to the parameter. We can integrate these along a curve, but that does not, to get GIs at different points on the curve, given some initial conditions on the curve. But unless the Riemann tensor vanishes, we cannot use this to produce vectors defined in the surrounding space, GI. Okay. Okay, any questions so far? That's a lot to absorb, but things will crystallize, become clearer as we make use of these concepts in the course. Okay, well, let's apply these geometric notions to the analysis of deformation. We're interested in classical physics, which entails deformations of bodies and materials in the conventional Euclidean space of our common experience. But nevertheless, we'll see that these geometric ideas afford some interesting interpretations of what's happening. So let's look at interpretations of deformation as a topic in differential geometry in Euclidean space. So here, for example, is a current configuration kappa t of a body. And since it resides in a Euclidean space, we can locate a point of the body, let's say a material point, using a position vector, small x, which, as we've seen in the beginning, is the value of a deformation function evaluated at capital X, which is the location of the same material point in a reference configuration, kappa r, say a fixed reference configuration. And I'll use curvilinear coordinates, theta 1, theta 2, theta 3, here, 3 coordinate curves passing through this point in space. Of course, these curves are densely distributed throughout the space so that through 3 coordinate curves pass through each point, each material point in the body. Okay, so we have a parameterization of the current configuration of the body. Why don't I do the following? Why don't I use the same coordinates to parameterize the reference configuration? That seems like a strange idea, right? So let's explain what I mean by that. Imagine painting a coordinate grid, curvilinear coordinate grid on the body in its reference configuration. You paint it on the body, then the coordinate lines become material curves. They're associated with a fixed set of mass points on the lying on the coordinate curves, right? So you can think of the coordinate grid as being painted on the body. As the body deforms, stretches and rotates and changes its orientation and so on, the coordinate grid stretches and deforms with those material points, with those material curves. So you think of parameterizing material curves using theta 1, theta 2, theta 3, and you can draw, say, here's an example I like to use at the bottom of the page here, of a balloon, inflating a balloon. So a balloon, think as a two-dimensional surface. We'll draw a coordinate grid on the balloon before we deform it. So we have a reference configuration. And let's say my material point has the coordinates 1, 2, for example. So at that material point, I just, with a magic marker, I write 1, 2 next to that material point. As I inflate the balloon, that coordinate grid gets stretched and rotated here. The copy didn't come out too well. So you have that coordinate grid stretching and rotating with the material points of this rubber balloon, let's say. That point P still has the label 1, 2 drawn next to it, right? The magic marker 1, 2 label persists in the current configuration. You still see it as being labeled 1, 2. So that's what I mean by this kind of parameterization. The coordinates convect with the deformation of the body. We call them convected coordinates, such that a given material point has the same label, coordinate labels. In this case, there are only 2 coordinates on a surface. Material point is perpetually identified with a single pair of coordinates, in this case 1, 2. Over here, this material point will have a different label, but that same label will remain with the material point in every configuration of the body. Is that hopefully more or less clear? So in that way, knowing the value of the coordinates tells you which material point you're talking about, and that the identity of that material point never changes. It always has the same name, theta 1, theta 2, theta 3. Okay, so I can use those thetas to parameterize position in 3 dimensions, as we've done up till now. And I can use the same thetas to parameterize position in the current configuration, except now, position will depend not only on the thetas, the material point I'm talking about, but it will evolve with time. The position will change with time as the body moves through space. So I have a 1-parameter family of parameterizations. Okay? So I obtain that by plugging into my deformation function, reference position given by a fixed parameterization not dependent on time. And then I have an explicit time dependence because the motion itself evolves with time, to give a position function for a given material point identified by its 3 convected coordinates perpetually. That position can change with time. Okay. So I think last time Malad was talking about a manifold that evolves with time, and this is an example. The body is a manifold parameterized by the theta 1, theta 2, theta 3. but its configurations evolve with time, and so this geometry will also evolve with time. Okay, so I need some notation to distinguish between the actual configuration at time t and a reference configuration. So I'll just import the notation we've been using up until now. I'll write small x comma I is small gi. Small gij is the dot product that gives the metric induced by the coordinates, the curvilinear coordinates g theta I. Small g is the determinant, positive as before, which guarantees the invertibility of these relations at any given time. So in other words, given the position, I can find the material point that occupies that position. So and then we'll, since we need a different notation here in the reference configuration, I use capital G's as capital X comma I, the same partial derivative, different function, capital X, but it's still a partial with respect to theta I. Metric, capital Gij induced by these dot products, determinant capital G, and so on. Okay. So we're taking the coordinates to be labels for the material points. These coordinates define a grid that convects with the body. The coordinate curves are material curves. And so this is a fundamentally Lagrangian description of the motion. I'm going to go with Lagrangian description. We regard the material points and time as the independent variables. And the material points are labeled forever by a fixed set of coordinates. So this is a fundamentally Lagrangian description of the motion. Okay, so in particular, since the material point is a material derivative, for example, when we take a material derivative of something, we're fixing attention on one material point. That means the convective coordinates are fixed when we take the material derivative. So the convective coordinates have zero material derivative. Okay. And these curves, as I already mentioned, are embedded in the material as material curves. Okay, so I hope that brief introduction to convective coordinates is clear. If you're learning the subject on your own, it's anything but clear. It can be quite a confusing thing to learn on your own. Convective coordinates are very popular in, for example, shell theory, because we want a coordinate system that stays with points on the surface as the deformation of the shell evolves. So it's a very good framework to learn. It opens up a lot of literature. So I think I better stop here, and next time we'll use these convective coordinates to analyze deformation and interpret our familiar deformation variables like the deformation gradient, strain, and so on in terms of this geometry induced by convective coordinates. Okay, if there are questions, please ask now. If not, I will see you next time. And as I say, I'll stay online if there are any questions about homework. Okay? If not, then I'll see you on Tuesday.
Question.
Yeah, is there a question?
About last time, you explained the Laplacian in the coordinate in the
curvilinear coordinates. Yeah.
Yes, and the Laplacian of a scalar phi is the divergence of gradient of phi.
Yeah.
Which is the trace of the gradient of phi.
The trace of the gradient of the gradient. Yeah, because the gradient of phi is a vector.
Yeah.
The gradient of that is a tensor, so we can take its trace.
Yeah. But how did you get that the gradient of phi is a gradient of phi comma I outer product G?
Okay. Okay, so we had gradient of v, vector v, is v comma I, tensor product G super I.
Yes. Both of
so just write gradient v equals gradient phi is gradient phi as a vector all comma I, tensor product G super I.
I'm sorry, I don't follow.
So v right
Can
V, replace V by gradient phi.
okay.
So you have to take the comma I of the vector gradient phi, which is phi comma j, g super j. Take the comma I of that whole thing, right?
Yeah, but like there's this formula that the gradient of a scalar times a vector is equal to the scalar times gradient of the vector plus the vector outer product gradient of the scalar. Yeah, one of these terms.
Well, we only have one scalar, phi. We don't have the gradient of a scalar times a vector. We only have in this formula for the Laplacian, we only have gradient of the scalar phi. And that gradient is itself a vector.
Yes.
Yeah.
Can you allow me to share my screen to show you? Like,
yeah. Let me stop the recording, and then we can do that.